Hello everyone and welcome to our presentation entitled Cholesteric Spherical Reflectors has Physical Unclonable Identifiers in Anti-counterfeiting. My name is Monica Arenas and it is a joint work with Huseyin Demirci and Professor Gabriele Lenzini at the University of Luxembourg. Along this presentation I will refer to cholesteric spherical reflectors as CSRs. So CSRs are cholesteric liquid crystals, the same material under the screen of our digital watches and television displays, just to mention a few applications. And however, in this application, they are molded into a spherical shape and hardened into a substrate. During the production phase, they are distributed randomly and they have a peculiar behavior when illuminated. They reflect light and produce unique optical patterns whose is hardly predictable. Previous works have argued that CSRs behave like physical unclonable functions, finding application in anti-counterfeiting, particularly in object authentication. However, a fundamental challenge remains open and is to understand what makes each optical response unique and how to extract this identifying information in a secure, robust and reliable way. For this reason, we propose a methodology to extract information from different datasets to calculate the intra and inter distance. For the intra distance, we have a set of 12 real tags from which we generated a set of retakes in order to make the comparison between the retakes and the real tags. For the inter distance, we have a set of simulated tags that we created, and then we also compare if exists any similarity between these simulated tags and the real ones. For the validation dataset, we follow the same methodology with different number of images. So let's take a look at how the images are, the real tags are, and we can observe that they have different colors, different CSR's density, and the illumination is also different due to the readout conditions. In order to understand what means the intra-distance, let's take a look at this image. And in each image we introduce rotation, blurring, cropping, and resizing, and then we compare each retake with its original image, with the real tag. For the interdistance, we have a real tag, and from this tag we extracted the blobs and the background, and then we built these fake tags, and then we compare if exists any similarity between this fake and the original one. We also compare it with another set of tags. And for the interdistance, we measure two important properties, that is the reliability and the security, that I will discuss in the next slides. And well, we defined three phases for the object authentication of the tags. The first one is the production phase. In this phase, we have the real tags, and we observe that they have different dimensions, different shapes, and as I previously said, the CSRs are molded into a substrate, and in this particular case into a polymeric matrix. The second phase is the path that we also subdivide into two parts. The first one is the readout phase, and this phase is extremely important because depending on the conditions, we have a certain response. For example, under the condition 1, we have the response. However, if we increase the intensity of the illumination, we have additional information that we couldn't observe under this condition. And if we challenge with a certain angle with respect to the tag, we can also have additional information such as these white spots. So the readout condition is extremely important because depending on it, we have certain kind of information. The second part of the path system is the extraction phase. In the extraction phase, we use image processing algorithms Firstly, to measure the alignment between the reference and the retake. So we initially measure the number of key points between them. If the number of key points is lower than 10, then the alignment fails, and meaning that the similarity between them is 0. Otherwise, we compute the alignment, then we convert the images into grayscale, and we compute the histogram matching. This transformation adjusts the pixel intensity of the alignment images according to the illumination and contrast of the reference image. Once performed this matching, we extract position and colors of the reference and the alignment image in order to compute the matching scores. That I will explain in this phase. So the matching phase said that the extracted information from two images, from the reference and the retake, matches if and only if the retakes belongs to the same reference image. And we implemented two algorithms for this phase. The first one is the similarity score, that, as I previously said, if the number of key points is lower than 10, then we have 0 in the similarity score. Otherwise, we compute the ratio between the number of served pixels over the total number of pixels. And this image difference is the difference between the reference image and the aligned image. The other score is the matching score, that is based on the minutia detection technique, which consists in extracting the relevant information, meaning that in our case is the position and colors. And this score defines when two blobs do match according to the relative positions of their circles and colors. Well, one important property is to measure the robustness, and the robustness is evaluated in terms of false negative ratio and interdistance between the reference readout and its retakes. The second property is the reliability, in which the system rejects any other responses generated by any other CRC tags. This property is measured in terms of false positive ratio and interdistance. The other property that we measured is the security, in which the system distinguishes and rejects images that are not taken from any real CSR tag. We can see in this image a clear separation between the intradistance and the interdistant cluster, and this separation fulfills the condition that the minimum value of the interdistance is higher than the maximum value of the interdistance, and this condition must be fulfilled in order to have a clear separation between both. As main results, we detected the blobs after the alignment of the images, and we observed that the number of blobs of each image is different due to the intrinsic characteristics of each one. And for the similarity score and the matching score, we observe that the matching score is constantly better than the similarity score, suggesting the hypothesis that the design based on minutia detection is more insightful and robust than the design based on image processing. And we can also see this result in these graphs. This graph shows that exists a trade-off between the correct authentication probability and false positive according to a choice of a threshold. For example, in the similarity score, this score is lower than for the matching score, and this result shows that the matching score performs indeed better than the similarity one. For the validation dataset, we choose a threshold of 5% for measuring the authentication probability. For the intradistance, we observe that both scores perform well, because the authentication one was 1 for all of them. And for the interdistance, most of them were 0. However, for the image 972, we observe non-zero values, and it is because the information of the faked images were based on this image. And these results suggest that it's important to implement another adversarial models in order to have to measure the strongest properties of the interdistance. Well, as summary, we can say that we implemented, tuned, and tested the procedures for measuring the accuracy, performance, and false negative ratio on a dataset of thousands of realistic and simulated responses. We extracted identifiers informations such as the positions and color of the blobs or CSRs. We also established a reliable, robust, and secure methodology. And our procedure also clustered images coming from the same tag, distinguished them from images of different CSRs or decoys. And we can also say that our work is one of the few that has studied procedures of information extraction in this kind of material. And it advances the state of the art in this area, closing the gap between the research on optical paths and practical application. As future work, we still have some work to do. The first one is on the readout phase because we introduced similarity noises such as the rotation, blurring, cropping, etc. However, it will be important to measure how our scores perform when introducing real noise. And this can be obtained by introducing Gaussian noise that it simulates the noise that arises during the acquisition due to the sensor noise caused by pre-illumination or high temperature or electronic or photonic noise. Another important future work is to measure the scores based on sigmoid or logit functions because our implementations is based on linear functions, so it will be important to observe how our scores behaves when using another functions. Well, and the other one is to implement better adversary models, as I previously said, because we use an adversary model simple, in which we have some information about one tag. So it will be important to implement another adversary models in which we have more information about the tags, such as the number of blobs, the total number of blobs with certain colors, or even modeling an adversary attack in which the attacker models the distribution of the shells in 2 dimensions. Another future work is to implement or to propose an authentication protocol for multiple and random challenge response combination. Finally, actually these 2 final works are ongoing. The first one is the deep neural networks, and this the idea is to classify images under different challenge conditions, and the second one is proposing secure sketches and fuzzy structures. Indeed, the secure sketch was already proposed and is under revision in another conference. And for the fuzzy structure, we are working on the security proof. Well, finally, we would like to thank to the Luxembourg National Research Fund for the project Security in the Shell and for the proof of concept No More Fakes. We will also want to thank Professor Yang Lagerwal, Yang, and Hakam for their valuable comments, feedback, and for providing the images. I will also want to thank for your attention, and I am open now to questions.